So maybe it is my glasses.
Anyone else want 5? And okay, so cool. I don't know what you did. I think it was something different than I don't know. I hope not.
Good morning, everyone. Good morning, Stockholm. I'd like to talk about homework number 5, which we're normally going to turn in today. But if someone would make a special plea, I might give you until Thursday to work on it. Would anyone like that extra time or not?
Well, it depends. Are we going to talk? If we're going to talk about it, and I find out I did something wrong.
Yeah, then you might change your mind. So let me talk. I'm going to solve the homework because I haven't worked out the details of it. I think I know the steps you must take, or you might take, to get a good answer. So let's talk about reversal. And these notes, if you'll note the date on it, these notes are from February 4th, so you should have this in principle somewhere in your files. So let's just talk about reversal and how we would model the reversal of a wing model, right? And so we have a wing, and we have a control surface. And we can model this at various levels, but I want you to model at the simplest level until it's not in practice, a wing rather than an airfoil with springs, right? Okay. So you need to use control virtue work. You do that, right? You need to write down the expression for virtue work, and that is going to be essentially the same as you had before when you did the typical section with springs, except now the aerodynamic forces are per unit span, right? Rather than now the potential energy, rather than being the spring constant times alpha squared times 1/2, is now a distributed potential energy, taking into account that GJ is the torsional stiffness of the wing. We still have the same expression for a moment about the elastic axis in terms of moment about the aerodynamic center, and lift. But now the moment about the aerodynamic center includes a constant term, which I allowed you to set to 0 for simplicity. But it also includes a term that is proportional to delta, because there's a moment about the aerodynamic center once you rotate the control surface. And then, of course, the lift has 2 components. It has a component due to alpha and another component due to delta. And we're trying to find reversal. Well, for one thing, this lift expression is per unit span. It's not the total lift from wing. It's the lift. Essentially, the lift per unit span is some span-wise location, because alpha depends on y. And you're going to have to find y in order to find the lift. But then the big question, which I hope you would sort out, and some people, well, I'm not sure anyone actually did, but some people at least asked the right question, came by, and I sent you an email about it. It's up to us to define what we mean by reversal in this context. But I think most people would say when the total lift is 0, the total lift on the wing is 0, that's what we mean by reversal. So what does that mean? That means we must determine the lift per unit span, and then we need to integrate that over the entire span and find the total lift, and then find out when it might be 0, right? And first of all, we have to find alpha, because we don't know alpha, we're never going to find the lift, right? So how do we find alpha? Well, we write down the equation of motion, which comes out of all this wonderfulness, right? We had that before. Then you substitute in the expression for the moment about the elastic axis, which means this is all expanded now. And now what is this? This is a differential equation, which if you tell me delta, or I pretend that for the moment I know delta, then I can solve for alpha. And one thing I definitely know just learned this equation before I do any arithmetic. It's a linear equation, therefore the relationship between alpha and delta will be linear. That means if I double delta, I'll double alpha. Okay? Or I triple delta, I'll triple alpha. And that means I only need to solve this equation for some delta, and then once I know that for alpha, I can find it for any other delta of interest. Because it's a linear model. And we're going to keep coming back to linear models because that's mostly what people use in industry. And mostly what people use everywhere but in science and engineering, because linear models are a lot easier than nonlinear models. Okay? On the other hand, those of us who do research, we have to do nonlinear models because almost all the linear theories. Yeah. So there's a dichotomy there. If you're teaching the course, you teach linear models because you got to walk before you run. But if you're doing research, usually you're dealing with phenomena. And occasionally we do that nonlinear, right? And even in this course. Okay. So we need to solve this equation. This is what I told you the other day for alpha. And when you do that, you'll find the alpha is proportional to delta. Okay. Then you need to substitute that back in this expression for lift. Remember, an alpha will now be, it'll be a function of y, but it will be proportional to delta. Therefore, the lift will be proportional to delta. The lift brings the span, but it will depend on y. But, you know, if I integrate the lift over the entire wing, I'll get some constants, which involves the dynamic pressure, by the way, times delta. Now, I want to know when that total lift is zero, what's when the coefficient of delta is zero, right? Because it turns out within the framework of a linear model, reversal occurs at a certain q, and it doesn't depend on the size of delta, since it's a linear model. If it were a nonlinear model, it turns out it would depend on the size of delta. But that's research. You remember Professor Bueno was writing a paper and saying it's research? Okay. So, that's what you need to do. I'm not sure anyone has done that as of a day ago, but maybe someone has done it in the meantime. Let me pause here for a moment. Because that's the essence of what I wanted to say, but there's a couple of things I want to say. Are you all with me? Yeah. And now, the question. You want 2 more days to work on this? Yeah, okay, fine. You've got until Thursday then to work on this. Question.
Logistical instruction. There's no resubmission. I'm going to set it so that you can resubmit your homework. Oh. And I'll change the deadline on the assignment on the time.
Oh.
So I won't process anything today. But
very good. Very good.
Okay, that's
fantastic. Okay. Stockholm, do you have any questions so far?
No questions from you.
Thank you. Okay, let's move right along. Now, let me confess, not really a big error, but a small error. When I was assigned this homework the other day, I was sort of reaching into my memory bank and looking at the equation. I left out the DCLD alpha term. And to make this non-dimensional and eliminate DCLD alpha, so you don't need to specify DCLD alpha. You need to incorporate that into the definition of the nonlinear cube. Right? But that's what we did before anyway. It's just I forgot to put it. And then I think you've got all the other numerics you need, and you should be able to write out an answer, and I'm looking forward to seeing it. Now, one thing, I haven't run the numbers myself. One thing you should be on the lookout for. Remember, there's something else that can happen in this model. There's another physical phenomenon that can happen in this model and arise from these equations. And the other major static aeroelastic phenomenon, in addition to reversal, is divergence. So it's conceivable, actually, that there's some numerical parameters where the divergence Q would be less than the reversal Q. Okay. If that's so, then I will need to do something to rectify that, but I would like you to take a reversal Q. And what would we change to ensure, if we really want the divergence Q to be definitely bigger than the reversal Q, what would we do? What of these parameters, what would we change? Which one would we change? And how would we change it? What? Not Q. What about example? The reversal depend on DC and AC d delta? Excuse me, the divergence depend on DC and AC d delta? No. So it's not that one. The reversal depend on DCL d delta? No. So it's not that one. Does it depend on E? Yeah, because remember what E is. It's the distance from where the lift acts, the aerodynamic center, to the elastic axis. And it's that lift that gives you a moment about the elastic axis that creates divergence. So if I were to set E to 0, I would drive the divergence Q to infinity, which probably means it's greater than the universal Q. So, just for fun, why don't you do two values? And by the way, if you want divergence Q to be less than reversal Q, what would I pick this to be? I pick it to be a big number. Right? Like 1. Right? That'd be a big number. In fact, that would put the aerodynamic center and the elastic axis off the lane. That's probably not realistic. But just mathematically, if I want the divergence Q to go down, I would make these bigger and bigger. Right? Okay. Right. Yes.
Reversal Q also depends on that, right?
You know, it turns out well, you're going to find out. In the, well, you're going to do two different values. But remember in our simplified model of the springs, the typical section model, not the wind, the typical section model, it turned out that the reversal Q did not depend on E at all. And you can see why, he said, Charlotte. Why? If I go back to this equation, if I set E to 0, there's no contribution to the lift, right? Yeah, so reversal is, and I'm trying, remember, well, let's put it the other way around. If I define reversal to be when the lift is 0, then this term will be 0, and there's no way that E will ever appear in my answer. I think that's probably still true, even for the swing model, because I haven't worked out the defect. Okay? Does that help? A little bit. Okay. All right. Now let's talk about extending this a little bit. Someone, maybe several someone, were thinking about using Rayleigh widths. And you can use Rayleigh widths to solve the homework problem. I would suggest that you do not do that. I'm not going to mark you down to do it. Great. But it's not the easiest way to solve the homework problem, and I assume the English prefer the easiest way. But remember, if all these parameters are constant, if Gj and so forth is constant, then you should be able to solve this difference equation analytically, right, in terms of sines and cosines of y. Right? Plus that. So that will be the homogeneous part of the solution for alpha, and then there will be an inhomogeneous solution, which depends on delta. Right? On the other hand, you could solve this problem, if you wanted to, by using Rayleigh widths. You could take alpha and expand it in terms of some modes, and I suggest that these modes become some of the modes that satisfy the boundary conditions. That's always a good set of modes to use. You could do that. And if Gj and C and those other parameters actually depended on y, there would probably be no hope of solving that differential equation analytically. You would have to use Rayleigh widths or something else. You could use finite limits. I wouldn't recommend that either, actually. But you could use finite limits. You could use Rayleigh widths. Okay. So if you use Rayleigh widths, no harm done. I'll look at it. You should get the same answer, provided you use enough terms in this series. If you don't use enough terms in the series, you won't get the right answer. But actually, you're probably going to prove an answer by using one term, I would guess. So, shall I ask you to do it both ways? No, you would probably don't want to do that. Okay. Okay. Pick your poison. Pick the way you like that. Okay. Anything about that? Anything more about that? Okay, you got 2 more days to 3 hours. And as long as I'm here, let me now that you have a greater understanding, you have a deeper understanding of all. Right? Let me go back to one other thing I said the other day. if you're really doing this for a real airplane, you probably wouldn't want to take into account the elasticity of the control surface. In the law I just discussed, I'm pretending like the control surface of rotation. It rotates like a rigid body. Delta is the constant all along the span. Well, if it's tied to the wing and the wing twists, it's unlikely that the control surface doesn't twist at least a little bit, right? So how would you account for that? Well, you would have to add something to the potential energy. You'd have to add not only the torsional stiffness of the wing, you'd have to add the torsional stiffness of the control surface. And then you have to account for how they're connected. And if they were connected by torsional springs or something that I can model as a torsional spring, I would have add additional terms to the potential energy that takes into account the relative rotation of the control surface compared to the wing, and it's that difference in rotation that would stretch my torsional spring, right? So I could make this a lot more interesting and elaborate. But you prefer I don't. But then you probably would go use grading bits again. Although you might be able to solve, you have two different difference equations. They both be linear. They would be coupled, and you might try to solve that out. Probably would be not impossible, but certainly more difficult than the simpler ones. Okay. All right. So when you are asked to do a divergence analysis later in your life, later in your career, you'll be up for it. Okay. Now, moving right along. We were going to now start talking about flutter. And this is the dynamic counterpart of divergence. And we're also going to talk about touch response. And to do that, first of all, we need to develop some equations of motion. And we agreed the other day that Hamilton's principle and Lagrange's equations are going to be our bedrock methodologies for doing that. To illustrate what can happen dynamically, I'm going to start with the simplest possible model. Namely, again, just our torsional model, right? Torsional model. And except we're going to add dynamics, which means we're going to add kinetic energy, right? So now we're going to have some additional terms in our equations in motion. So let's see. Let's go back to our typical section model. Let me draw a picture so you know what I have in mind. Our typical section model is this model with the torsional spring. And so the potential energy is still 1/2 times of alpha squared. And I suggested that the kinetic energy could be written as 1/2 the moment of inertia about this axis times alpha dot squared. Oops, not integral. And then there's virtual work, of course, which with this model is m sub y times delta alpha. And m sub y, as before, is the moment about the aerodynamic center, which by definition doesn't depend on alpha, plus the lift times E. And the lift, in this case, is just Q area of this perceived simple wing times dCl d alpha times alpha. But now, because we're doing dynamics, we want to recognize that this lift might not only depend on alpha, but it might depend on the time derivative of alpha, on alpha dot. Actually, formally, it depends on alpha dot, alpha double dot, so forth and so on. But we'll use the simplest extension, dCl d alpha dot times alpha dot. Am I still on the page? Yes. Okay. And this term will make all the difference. And now, how am I going to derive the equations of motion? Well, I can use Lagrange's equation. We're calling the Lagrangian. Never, ever to be confused with the lift. If you want me to, I'll put a little A on it to be Lagrangian. Anyway, this is T minus U. And now our Lagrange's equation is d dt with the partial of L with respect to alpha dot minus partial of L with respect to alpha equals, I'm going to call it Q sub alpha. And what is Q sub alpha? Q sub alpha, by definition, is the thing that multiplies del alpha in an expression. This defines Q sub alpha. So the way this works in practice is I have to be able to compute the virtual work using some physical and mathematical reasoning. And it will always turn out to be something times del of, in this case, alpha. And this coefficient is Q sub alpha. But then if I look back at this expression, which came from physical reasoning, right? And I compare these two, then I conclude that Q sub alpha must be equal to M sub y in this case. In other cases, the relationship will be a little more elaborate. But that's how I find the Q sub alpha in Lagrange's equation. I construct a physically and mathematically valid expression for virtual work, and then identify the coefficient as Q sub alpha. And this is usually called a generalized force. You can call it anything you like, but most of the world calls it generalized force. Okay. Okay. Now, I also have to compute DL, this is Lagrangian now, right? The alpha. Well, the only place where alpha appears in the Lagrangian is in the U term, which is here, right? So these LA d alpha is just 1/2 2 K sub alpha times alpha, right? So it comes out to be what you would expect it to be, right? And on the other hand, DCL d alpha dot is 1/2 from here, 2 I sub alpha times alpha dot. And all this turns out to be what you might expect it to be. And then when I take d dt of that, of course I get I alpha double dot. This comes out to be what you would think it might. And then recognize the following. I've got a minus sign here, but there's another minus sign here. So it comes out to be a plus sign as it should. And since I know the answer. And so the equation of motion then is I alpha double dot plus K alpha equals Q sub alpha, which we decided was M sub y. So this is the same equation I had before, except now I have an inertia term here. And in M sub y, I'm sorry?
Yeah, what?
This is a plus, yeah?
No, I mean, what? Minus?
Well, this term is minus?
Yeah.
Well, it came out to be plus. There was a minus sign here, and then L sub A is T minus U. So there's a minus sign here and a minus sign here, and they annihilate each other, and I end up with a plus sign. Okay? But now remember, M sub y itself depends on alpha and alpha dot, right? So let's write that down. So I have I alpha double dot plus K alpha equals M sub y, but that's equal to Q C, and I'm going to assume that CMAC is 0, if you'll permit me to do that. And this is then going to be DCL d alpha times alpha put DCL the alpha dot times alpha dot. And now I'm going to put all this on the left-hand side, if you'll permit me to do that. I alpha alpha double dot plus K alpha. And now I have an alpha term here, so minus QC DCL the alpha all times alpha. And then minus QC DCL, oh, excuse me, I've been saying C, I really should have put area here, so to be consistent in my notation. DCL the alpha dot times alpha dot equals 0. Now these things are constants, right? At least for a linear theory. And I need some aerodynamicists to tell me what they are.
What's the term before the DCL, the alpha dot? Is it S?
This is S, yes. I kept making it a C, and I'm thinking of Jeffrey and Span, but I probably should make it area to be consistent with earlier notation. Just make it 0 to be a C. Ah! There certainly should be. Thank you. Okay. Now, what can this equation tell us? Well, first of all, from a dynamic perspective, and it can tell us that divergence is a possibility. Why is that? Well, this term can change sign, right? If Q gets large enough, this term will become negative. And that implies basically I have a negative stiffness. You might think that a system with negative stiffness would have a static instability. Or, more formally, you could do the following. You could say alpha, I'm going to look at alpha, I'm going to assume some magnitude which I don't yet know, times e to the, be careful of my temptation, beta t, and I don't know beta, and I don't know alpha bar. But my course in differential equations, and probably your course as well, said that if I want to solve this differential equation, it's a differential equation in time, right? I can assume this form, and then I can determine the possible betas, right? And then I can also determine the possible alphas. The alpha bars will be determined from initial conditions. That is, I have to specify alpha at time t equals 0 and alpha dot at time t equals 0, because this is a second order difference equation, right? But I don't really need even to do that to determine stability. To determine stability, all I need to do is examine beta, right? And what can happen? Well, beta in general will be a complex number with a real part and an imaginary part. It's the real part that tells me whether I'm stable or not. If the real part is positive, this is exponentially growing in time. That's an unstable system. If beta is negative, it's decaying in time. The imaginary part basically gives me the frequency of an oscillation. So this thing is in the form of a complex exponential, right? It's e to the beta r times t times e to the I beta I times t. So this part tells me about the oscillation and the frequency of the oscillation, namely beta I. And this part tells me whether I'm growing with time or decaying with time. All right, so let's do that. Let's substitute Cohen's equation 1, 2, 3. Let's put 3 in equation 2 and see if we can determine the betas. We can, all right. Every time I have a dot, and I differentiate this exponential, and I get a factor of beta, right? And then there's going to be a common factor of alpha bar and everything. Well, one solution would be alpha bar equals 0, but that's not very interesting. And would not satisfy any non-zero initial conditions. So I know alpha bar equals 0 is not the interesting clinical condition. So what I want to do is find when the rest of it can be 0. So I'm going to have beta squared times I alpha plus K alpha minus QCE. That's important. Thank you. DCL D alpha. And there's no beta here because there's no time derivative. Plus, minus QSE DCL D alpha dot times beta, because this is alpha dot, right? So I get a factor beta equals 0. So the non-trivial solutions are the values of beta that satisfy that condition. This is sort of like the mathematics of what we're doing in statics, except now the physical context is quite different. Now we're talking about time evolution, right?
Can you move it up a little bit? It's just a little out of focus.
Does that help? Okay. Okay. So let's look at a couple special cases, and then we'll go on from there. First special case is I'm going to assume that this DCL D alpha dot term, which I took great pains to include, I'm going to set to 0. Right. If that's true, then we just have I alpha beta squared plus K alpha minus QCE DCL D alpha equals 0. Right? And now using higher mathematics, beta squared is equal to what? Well, I can write this a couple of different ways. Well, let me do it the obvious way. I'm going to take all this and put it on this side, right? And now, so I have, and that will introduce the minus sign, right? So I have QCE DCL D alpha minus K sub alpha divided by I sub alpha. That's beta squared. Okay. Now, if Q is 0, or if Q is small, how small? Small enough that this whole thing is a negative, because I have minus K alpha, right? If this thing is small, then this term dominates, and beta squared will be negative. Beta squared will be negative. If beta squared is negative, then beta is equal to plus or minus a positive number, right? It's a many. Beta will be a purely imaginary number, which means if I go back to here, it means I have a pure oscillation. Doesn't grow with time, doesn't decay with time. I have a pure oscillation. So, well, what I call that a stable system or an unstable system? Okay. Well, it depends. So that's a good answer. What does it depend on? Well, when we put the beta term back in, we'll see if it's a little margin in. But strictly speaking, this is neutrally stable. What does that mean? It means we can't make up our mind. It doesn't decay, doesn't grow. It's not going to become unbounded. Yeah? And it's stable. So it's neutrally stable. That's what people usually say. On the other hand, if Q gets big enough so that this thing changes sign, right? So this whole thing is positive, then beta squared is a positive number, and beta itself is plus and minus a positive number, right? Okay, so let me draw this. If Q, C, E, DCL, D alpha minus K alpha is less than 0, that's neutrally stable. That's what we just discussed. Okay. On the other hand, if Q, C, E, DCL, D alpha minus K alpha is greater than 0, then beta is either plus or minus a positive number, which means if I go back here, I have two solutions, one of which is growing exponentially with time, and one is decaying. Well, if I let time evolve, the exponentially growing solution will dominate. In fact, according to this model, it goes off to infinity. This is an unstable system. That's divergence from a dynamics perspective, right? Because when this coefficient is exactly 0, that is the divergence condition we saw from our static analysis.
So if beta can be positive or negative, then are the solutions additive?
Yeah. Yeah. The total solution. There's always two guys. I'll call them beta 1 and beta 2. Okay. So the total solution for alpha, if you can write this way, alpha bar 1 times e beta 1 times time plus alpha bar 2 e beta 2 times time. Beta 1, beta 2 being the two solutions. Now, how would I determine these coefficients? Well, I would have to apply the initial conditions, right? But if I'm only using the stability of the system, I don't need to bother with applying the initial conditions. All I need to find out is whether one or the other of these solutions is growing or not. For the system to be stable, completely stable, both of these exponential factors need to decay with time. If one of them decays with time and one of them is nuclear stable, but one of them just oscillates with time, I call that nuclear stable. Actually, in the case we just saw, they were both oscillating in time, right? They were both nuclear stable.
Are alpha bar 1 and alpha bar 2, are they both positive?
No. In fact, they only need to be real numbers.
Yeah, but I mean, if one is negative and one is positive.
You think they might cancel somehow?
Yeah.
Well, not really. If this one's exponentially growing and this one's exponentially decaying, this solution is going to dominate, right? This solution is going to dominate. I only need one exponentially growing solution for the system to be completely unstable.
Yeah, but what if beta 1, is it possible that beta 1 and beta 2 are both positive and alpha 1 and alpha 2 can have opposite signs?
Well, I suppose that's theoretically possible. I've never seen that happen, but yeah. In this case, that's not what happens. In this case, remember what happens. Beta 1 will say be greater than 0, and beta 2 will be less than 0, and this one will decay, and this one will grow. Yeah, I suppose. You know, you could think of aligning the initial conditions just so. But remember, in a real physical system, I don't control the initial conditions. That's controlled by Mother Nature. And so the chances of Mother Nature being kind enough to take two potentially unstable solutions and having them cancel is not high. How's that? All right. But now, in all this so far, I've left out that beta term that came from the alpha dot. Now, so let's go back and look at that. If we may. I'll rewrite this. I keep putting C down. I really should put S down. You're too kind to correct this, right? I'm going to correct my notes so you'll have it in the right notes. You can, every time you see a C, please put in an S. I could define S is equal to C, I suppose, but that might be cheap. Okay. Then I have minus QS E ECL E alpha dot times alpha dot equals 0. Now, let's rewrite this in the following way. Have beta squared plus K alpha minus Q S E ECL D alpha over I alpha minus Q S E ECL D alpha alpha dot alpha over I alpha equals 0. Now, I'm going to remind you of something that hopefully you all know. This is a different physical system that has a similar equation of motion. if I have a mass on a spring, right, and also there's a dash pod, which is the symbol that we usually put in to represent some form of damping. And I call the displacement of that spring X, and I call the mass of the spring M. And I think you recall that the equation for that spring is mx double dot plus kx plus cx dot equals 0, where this is some measure of damping in the dash bar. Right? Or sometimes you see this written in a different way. Sometimes it's written as x double dot plus the natural frequency times x plus twice, you'll see why the 2 is there in a moment, times a damping coefficient, which is non-dimensional, times the natural frequency times x dot equals 0, where omega n squared by definition is k divided by m, right? That's the natural frequency of the squared of the spring. And then, C is equal to m2 zeta omega n. I guess that's it. This is a small c. Okay. So you've all had occasion to take Professor Keel's vibration course. You probably looked at this example, right? Well, our equation is essentially the same equation. Okay. We have a spring, except it's a torsional spring. And we have an alpha dot term, which arises from the aerodynamics, not from some dash pod oscillator, right? And so all the things we know about this equation can be used to interpret that equation. Yes, sir.
Rather than having beta squared, then alpha double dot.
Say again?
In your equation motion range, shouldn't we be looking at alpha double dot rather than beta squared? So you substitute beta.
Oh, I'm sorry. Sorry about that. This should be beta, right? I've already taken alpha dot and replaced it by beta times some factors. Thank you. Yeah. Or if you want to write this back in terms of alpha, alpha double dot plus this thing times alpha plus something more times alpha dot equals 0, right? Sorry about that. Okay. So the point I want to make is this term is damping. This is a damping term. And you probably realize that whether this solution is normally damped, right, for this case, when C is a positive number. If C ever becomes negative, I have a dash pot with negative damping. And in aerodynamics, in the aerodynamic flow of a ring, the damping can indeed become negative. Okay. And so, if I interpret, I can write down the solution for this equation by analogy to the solution for that equation. The solution for this equation is x equals x bar, again, e to the beta t, right? And now, if I substitute that into here, what are the possible values of beta? Well, there's beta squared plus omega n squared plus 2 zeta n omega n beta equals 0. So again, this equation looks a lot like this equation. And now if I solve for beta, using the quadratic formula, it is what? It's minus 2 zeta n omega n plus or minus 2 zeta n omega n squared minus 4 omega n squared square rooted over 2, right? That's a quadratic formula for this particular equation. But now you see, here's why you can see now why I introduced the 2 up here, right? I knew I was going to get there. So now, what is this equal to? It's equal to minus zeta n omega n plus or minus, I have omega n squared. These four factors, when square root are going to cancel that too, plus or minus zeta n squared, right now room here, sorry about that. Let me write over here. Beta is going to equal minus zeta n omega n plus or minus zeta n squared minus 1 times omega n. Right? That's what beta is going to be. But zeta n normally, for most systems, is a number that's small compared to 1. This is square rooted. And therefore, it's going to be an imaginary number when I take the square root. In fact, often one neglects that term entirely because it's so small. Right? So very approximately, not too approximately, this is minus zeta n omega n plus or minus I omega n. That's beta. If there's no damping in the system, if zeta n is 0, then this is just an oscillator. Right? And if zeta n is positive, it's a damped oscillator. And zeta n is not. But if I go back here and I look at this coefficient in this term, if this is a positive number, and I have a negative number here, then I have negative damping. That's the point. I have negative damping. And I can easily have that in an aerodynamic flow. The aerodynamic damping can actually either be positive or negative. And it usually depends on the value of Q, and this coefficient depends on Mach number. And a low Mach number is normally such that this is a negative number and it's positive damping. But if I get up into the transonic regime, that coefficient can easily be positive. And I can have negative aerodynamic damping, which means the system can be unstable just due to the negative aerodynamic damping. And there's a famous set of applications in the turbo machine where that happens. In fact, I'm told, most turbo machine flutter analysis is just about determining the sign of that term. Right? And that's why you need to run the CFD code. Just to find the sign of that term and how it varies with Mach number. And if I have multiple blades, then there's interphase, blade angle, and all the rest of it.
So a lot of work seems just focused on finding the sign of the term.
Yeah, that's why you were working.
No. So are you aware of any computational efforts that focus on the magnitude of the term?
Oh, sure.
Really?
Yeah. Well, because, see, in this model so far, I didn't put any structural damping in. Okay? So if I had some structural damping, and it was positive, then it might offset the negative aerodynamic damping. And people, when they design turbo blades, they put in structural dampers and use the structural damping. And one reason they do that is to offset the possible negative effects of negative aerodynamic damping. Yeah. Absolutely. So, okay, but that's not the only possibility for flutter. But this is one example of flutter. So people talk about single degree of freedom flutter. Why single degree of freedom flutter? Because we only have output. We only have 1 degree of freedom, right? Single degree of freedom flutter due to negative aerodynamic damping. Okay? But now let's make things a little more interesting, at least conceptually. Now let's go to our wing model. Well, we could do the same thing for our wing model. Okay. But now it would no longer necessarily be a single degree freedom flutter because our wing is an elastic structure. has lots of modes, right? There's the first mode, the second mode, the third mode, all. And so in principle, you need to look at each mode and the possible sign of the magnetic damping of that mode and determine whether any of the modes can be dynamic and stable. And again, it's very much like what we were talking about a moment ago in a slightly different context. It only takes one unstable mode to make the whole system unstable, because if there's one unstable mode, over time, that mode will grow in amplitude and all the other modes will decay away, and that will be the dominant solution. So one unstable mode is sufficient to make the whole system unstable. Well, that's a little bit of a complexity. Why? Because even though these systems in principle have an infinite number of modes, you can't check that many, right? So some judgment is required. And normally one hopes, and in practice one often finds that the lower modes that are most critical. The higher modes, in fact, sometimes you can do an acid-type analysis and show that all the modes beyond, say, the 10th mode are stable. But that's not always the case. There are cases where our high modes are unstable. And in an airplane, there are the modes associated with the horizontal tail, the modes associated with the vertical tail, the modes associated with the wing, and then the overall modes, because all these things are connected together through the fuselage. So there are a lot of modes potentially. All up front analysis of real airplane, people might use dozens of modes in the models, and they have to track all of them. Okay. Let's see, one of them, it only takes one. Most of them might go mistake. And there are famous incident cases where people have missed the mode. Right? They missed the mode. And they only found it when they did a wind tunnel test, or they did a flight test. That's not a good thing. Okay. Now, the symmetry of freedom clever case allows us more or less to look at each mode individually, right, one at a time. And that's, I think, typically what is done in turbo machinery. Not always, but often. In airframes, there's another kind of flutter, which requires at least two modes. Otherwise, it doesn't happen. So the other classical form of flutter is called coupled mode flutter. It has various names. And it's coupled mode flutter is one name. It's sometimes called bending torsion flutter, because it turns out it takes one bending mode and one torsion mode for this kind of flutter to happen. So you see that. It's sometimes called coalescence flutter. Why would it be called that? Well, it's because if you think of the modes each having a frequency, as Q increases, those frequencies come together, they coalesce, they meet at some point. And near the Q value where those two frequencies come together, that's usually a flutter condition. Not universally, but often. And so it's very characteristic if you trace the frequencies of modes in a wind tunnel, as I'm increasing the wind tunnel flow velocity, dynamic pressure. You'll see those two frequencies tending to come together. And when I see them coming together, I know I'm probably approaching a flutter. The other way you can track in a wind tunnel test or any experimental test, you can try to track the amount of damping in the mode, right? It turns out measuring the damping in the mode is a lot harder than measuring the frequency, which is not easy either, but by comparison. And it's easier to see the change in frequencies than the change in damping, because when you try to measure damping in a real experiment with noise and all the rest of it, the damping values are not very repeatable, and there's a lot of scatter. So I'm trying to plot damping versus Q, and there's a fair uncertainty at any given Q value what the damping actually is. So therefore, I'm having trouble trying to track the damping as it moves along. Okay, so in order to do this kind of flutter, we need at least 2 degrees of freedom. Okay? And what 2 degrees of freedom do we need? Well, we need a bending mode and a torsion mode. The classical example, this is in the book, which I'm not going to discuss since you can do it in the book, right, is I have my torsional spring again, but now at the same point, I put a translational spring. So this represents torsion, if you will, or twisting. And this represents, I'll put in parentheses, bending. It's really translation on the spring. So you can develop the equations of motion for that case, and I'll let you read about it in the book. And we will move right along and do the wing case straight up, right? There's no point in fooling around. You're agreeable? Okay. How about you, Stockholm? Is that all right with you too?
Yes, perfect.
People are so good to work with. Yeah. Okay. So here's our wing, and here's our elastic axis for this one. And now we're going to let this wing have twisting about the elastic axis. But we're also going to allow for bending of the elastic axis. And to get coupled both flutter, we need to allow for both. So what do we need to do? Well, we need to write down the equations of motion, which means we need to write down virtual work, potential energy, kinetic energy, and all the rest of it, right? Let's do it. I'll do the easy one first. Virtual work. Let's see, alpha of y and t, we're doing dynamics, right? So alpha depends on y as well as t. That's the twist about the elastic axis. And h, which depends on y and t, is the bending, or if you will, the translation of the elastic axis.
Excuse me, could you move it a little bit to the left?
Sorry, thank you. Thank you. No, sorry, I gotta have it down. I lost the ball. I lost my chart here. Okay, so this is now going to be m sub y, delta alpha, dy, where this is the moment about the elastic axis per unit span. Right? But then, I also have some virtual work associated with the H deformation. Okay. And that's the integral of the lift, right? Times del H dy. And now I'm going to put a minus sign in because everyone else does when they do this problem, even though it's maybe not most logical thing. And the reason I have a minus sign is I'm going to define H as positive down, which is what aerodynamicists do. Aerodynamicists sometimes cause trouble. This is one of the mistakes.
Are you an aerodynamicist?
Well, sometimes I am. It depends on which day of the week you talk to me. Sometimes I'm an aerodynamicist, sometimes I'm a structural dynamicist, sometimes I'm just a dynamicist. I'm really just a dynamicist. It's all the same, the fluid solid. L, on the other hand, is positive us. Okay? And this is the convention that people use in this field. And that's why there's a minus sign, because they're trying to positive in two opposite directions. Then I think you use the minus sign and make it all of that. Okay. Kinetic energy. I'm going to write this in an apparently more complex form. I'm going to write it this way. I'm going to define a coordinate x, whose origin is at the elastic axis and is positive for the trailing edge. Again, this is the sign convention that people use. So I'm going to write this now as the mass per unit area. Times W dot denotes time value, where W depends on X, Y, and T squared dx dy. What is W? W, just to make life difficult, is positive up, and it's the deflection at any point whose coordinates are X and Y. Okay? Now I'm going to write W in terms of H and alpha, right? And so the way I've set things up, W is minus H. Remember, W is positive up, H is positive down, hence the minus sign. Minus alpha, which depends on Y and T, right? Times X, right? This is the deflection of any point due to the twist. This is the deflection due to the bending of the elastic axis.
Deflection being in like the.
Well, I'm sorry about this, Stockholm. I'm going to do a visual here. Well, maybe I can. Here's my wing. W is the deflection of any point on this wing positive up. And this wing has deforms because it bends and it also twists about the elastic axis. I can develop a more general theory and go up in the function motion directly in terms of W, but we're not ready to do that yet. Well, I'm pointing out that to get the kinetic energy, I went back to earth, fire, wind, and water. I went back to the basics. I went back to kinetic energy is always 1/2 the mass times velocity squared. And if this is mass per unit area, then I need to integrate over the area. Right? So I can think of this mass per unit area as what? So this is the material, if this is a solid wing. This is the material times the thickness. Right? That's what it would be. The mass per unit area. Okay. Okay. So now if I substitute this in, I can get an expression for T. That's going to be 1/2 integral with respect to Y of H dot squared. Right? If W is this, and then I take a dot of W, I dot H and I dot alpha, right? X doesn't depend on time. So when I put this in, I'm going to get an H dot squared term, I'm going to get an alpha dot squared term, and I'm going to get a cross product. I'm going to get an H dot times an alpha dot, right? And the way Went normally writes this is 1/2 M H dot squared plus 2 S alpha integral of, oops, put side integral. I've got one more sharp pencil, but let me get near the end of the lecture. S alpha H dot alpha dot dy plus integral I alpha alpha dot squared dy. And what are these? Well, M will be just the integral of M dx dy, right? Yep. Not dy. So we end up with, because this is mass per unit area. I integrate once, so that'll be mass per unit span, right? I alpha will be the integral of mx squared dx, and S alpha will be the integral of mx dx, right? So these are integrals along x, right? These are integrals along the point. So this is the mass per unit span, this is the moment of inertia per unit span about the elastic axis. And this is, what is this? What is that? We call this moment of inertia, but this is really the second moment of inertia. This is really the first moment of inertia. And I can write this in a different way. I can define a new symbol, which is M, right? That's this M, times X sub CG, right? This has the units of mass per unit span. This has the units of mass times length squared per unit span, or moment of inertia per unit span. This has units of mass times length per unit span, right? And if I define this interval to be this times this distance, what is that? Physically, what is that distance? He said, Charlie. Yeah, that's right. It's the distance from the center of gravity at any position along the span to the elastic axis. If the center of gravity is at the elastic axis, then this term's going to be 0. It turns out for this coupled mode flutter, this term is really important. It's one of the most common ways to solve a flutter problem is to change the value of S alpha, as we'll see. We'll see why that's so. And what you want to remember is you put the mass ahead of the elastic axis, not behind. If you want to flutter, you put the mass at the trailing edge. If you want not to flutter, you put the mass at the lead edge. And so one of the most common ways to solve the coupled mode flutter problem is put the mass in an appropriate place. Okay? That's the good news. Bad news is the chief engineer is upset because you've added mass to this fine airplane, which has degraded the performance, right? So when you put in a couple hundred pounds of mass to solve a flutter problem, the chief engineer says, well, I can't repeat exactly what the chief engineer would say, but he says you're a bad person. But he usually doesn't use quite that language. You say, you did it again. I have a perfectly nice airplane now. I have to add mass just to solve your problem. It's not his problem. It's her problem. It's the counter engineer's problem. Okay. Okay. So now we've got
Hello?
in terms of H dot. Yeah, oh, sorry, yes.
Yeah. Can you tell me, like, for the flutter case, where should it?
Did you understand what I said? Would you say that again, please?
For the flutter case, where should we put the mass again? At the leading edge or at the trailing edge?
Yeah. Well, we don't know this yet because we haven't gone through the flutter analysis, but I'm giving you a preview. If you want the flutter not to occur, you usually put the mass at the leading edge. On the other hand, if you're doing a flutter test and you want to examine flutter because you find it fascinating, you'll put the mass at the trailing edge.
Oh, okay.
Okay.
So it depends upon the analysis later on.
Okay. Yeah, it'll come out of the analysis. Okay. So now, finally, we're now going to do the flutter analysis. But finally, we'll have to write an expression for U. And U before was 1/2 the interval of Gj. Now I'm going to write it as partial of alpha with respect to y squared, dy. It's a partial because alpha now depends on not only y, but also depends on time, plus something else. 1/2 integral dy EI, which is the bending stiffness of a beam, because I'm treating the elastic axis like it's a beam, times the second derivative of h with respect to y squared. This is the potential energy of a beam. Okay? This is the potential energy of a torsional rod. So I'm treating this wing as it has pure twisting about the elastic axis and pure bending of the elastic axis. And one reason we choose the elastic axis to do all this wonderfulness is because if I do that, then in this expression for U, there's no coupling between alpha and h, right? The terms appear separately. There's no cross term, right? There's no derivative of h times some derivatives of alpha. Now, if I had chosen as my axis system the center of gravity, there is a center of gravity axis that moves along the thing. Then there would have been any coupling in the kinetic energy terms. But now there would be coupling here. And because these expressions are usually more complicated, you usually say, I'll pay the price of increasing the complexity of my kinetic energy expression to save myself some effort when I write down potential. But now I have all the ingredients, right? I have potential energy, I have kinetic energy, I have virtual work. Now I can use Hamilton's principle, or I can do Hamilton's principle and derive two equations for H and alpha, which will be linear partial differential equations. And I know they're going to be linear. How do I know that? Because the expressions for kinetic and potential energy are quadratic in H and alpha. If they're quadratic in H and alpha, why decipher how many time and spatial differences are going to be? As long as they're quadratic, I know I'm going to end up with linear equations. Right? So I'll end up with two linear partial differential equations because both H and alpha depend on y and time. Okay. Or I could use Rayleigh Ritz. I could take alpha, a function of y and t, and write it now as a summation over n of a sub n times alpha and n of y. But now I'm doing dynamics, so the a's have to be functions of time. And h of y and t, another sum, I'll use a different index, m. Well, let's call it r. Because m, you might confuse m with mass, right? R, b sub r, a function of time, times h sub r of y. Of course, I have to determine those modes. And what we normally use are the natural modes of the system. Those are the modes that occur when I set all the aerodynamic terms to zero, right? Those are the natural resonant modes of the structure. That's what you universally use if you know them. And usually you make some considerable effort to determine them, either computationally or you might go in the lab and actually measure the natural modes of your structure. In fact, you probably will at some point. Then compare your computation and your measured modes, and they don't quite agree. And so what do? You adjust your computational model so that they line up in some rational or irrational manner. Okay, I think we'll stop there. So have that in mind. Read Chapter 3 if you have not done so already. And you might want to read the part of flutter analysis for the typical section with the springs, because I'm not going to cover that part. You're on your own. Okay.
So as a reminder, homework 5 will be due Thursday, and resubmissions on Sakai will be allowed. If you've already submitted, your submission is there. If you want to resubmit, go right ahead. We'll have to resubmit. We got have to.
I know we've got the new submission.
Oh. Yeah. Don't worry about it.
Okay, any questions before we leave for today?